Hello and welcome to this series on videos where I'm going to go over the normal distribution. We have already discussed those distributions that are binomial and geometric. Those are the two distributions that you are expected to know for the mathematics A-level course regarding discrete random variables. So now I'm going to start this by making a small comment on what we understand when we talk about a continuous random variable. And to begin with, the idea is that this new variable that we're going to be considering can take virtually any value within a certain range. For example, imagine that you want to measure, you want to calculate the probability that a certain bus is going to arrive to your bus stop in the next 10 minutes. Well, the variable that measures minutes is a continuous random variable because you can have 9 minutes, or you can have 8 minutes, or you can have 8 minutes and a half, or you can have 8 minutes and 10 seconds. You can always make divisions between any value that you want. So in that sense, we're talking about a continuous variable. So what is going to happen now with continuous variables? Well, with continuous variables, we are not going to calculate probabilities that are equal to a value. Okay, for example, we are not going, in the example of the bus stop, I cannot calculate the probability that my bus arrives in exactly 8 minutes, because the probability that my bus arrives in exactly 8 minutes is equal to 0. Okay, because it can arrive in 8 minutes and 1 second, it can arrive in 7 minutes and 59 seconds, and those probabilities, those exact probabilities are always equal to 0. Why is it that we are going to consider, what is it that we're going to consider? We're going to consider values with intervals. So if we have a continuous random variable y, we are only going to be calculating the probability that this value of y is less than a number, this value of y is greater than a number, and the value of y is between two numbers. So for example, we can say, well, what is the probability that my bus arrives in less than 7 minutes? Or the probability that my bus arrives in between 6 and 6.5 minutes. That those are probabilities that we're going to be studying, and not the probability that these are exact, because the probability that these are exact is going to be 0. Having said this, we're going to take a look at what we understand as a probability density function. And this probability density function is going to be considered as the function that will tell us about probabilities in the most graphical way. Okay, we're not going to be working with functions themselves, but you need to understand that these continuous variables have a function, have a graph that we can use to show probabilities in some way. And these functions, we're not going to get into deep on what these functions mean. This relate to the actual definition of what a continuous variable is, but we're not going to get into that. But what I want you to understand is that whenever you have a probability density function that we're going to call PDF, okay, what we know is that the area that is under this curve has to be equal to 1. Okay, for a function to be called a PDF, a probability density function, the area beneath that curve has to be equal to 1. So essentially what we're doing here is we're taking all of the probabilities for all of the values in between, okay? And all of that we can consider. So imagine, for example, that we could have, where we were considering the bus, we could have, okay, this is from 0 to 1 minute, from 1 to 2 minutes, and so on and so on. So we could consider, like, okay, all the possible values, and that area will be telling us about the probability. The thing about this, before you get like a bit worried, we are not going to be working with integrals for this part of the paper. Okay, this paper that had this probability statistics, does not include integrals. Formally, in mathematics, you would eventually sum probabilities calculated via integrals. This is not the case, and we're going to see why in a few minutes. The thing is that uh, we need to understand that our probability, the one that we're looking for, is going to be an area, okay? And all of these areas that we have here must sum up to 1, okay? This is what I want you to get from here before we move on to what comes next. What comes next is a reminder on what we called a function or a distribution to be skewed. We talked about skewness when we discussed data in one of our first topics that had to do with when data is not symmetric. Okay, if you look at this graph that we have, this PDF that we have here at the middle, I believe that you can see that this is a symmetric curve with even tails. And then we had negatively skewed data that had a tail that is longer to the left, and positively skewed data that had a tail that is longer to the right. The interesting thing about this is that this peak that we see in the PDF always corresponds to the mode. And the thing that will characterize the normal distribution has to do with this symmetry. So what do we talk about when we talk about a function that is normal? We're going to say that a distribution is normal, a probability distribution is normal when the mean has the same value as the median and has the same value as the mode. This is the condition so that we can say that our probability distribution is a normal distribution. Okay, clearly a continuous one. The peak of the curve, the one that we just saw, is going to be equal to the value for the mean. And there is where the line of symmetry of the curve will lie. As we move away from the mean on both sides, the probability is going to decrease, meaning that the further that the values we're looking for are from the mean, the less likely they are to occur. The probability is going to be lower. And if we have an increase on the standard deviation, this means that the value will be more spread. Okay, so let's take a look at this with some examples that I believe that will help you understand what we're talking about. Here we have two graphs of two different scenarios comparing normal curves. If you look here at curve A and curve B, you can see that the peak is located at the same value for x. What does this mean? This means that the mean of A and the mean of B are the same because the symmetry and the peak is at the same value for x. Now, if you look at the shape of the curve, this curve is more widespread, while this curve, the one for B, is more compressed, it's more close to each other. This means that the standard deviation of A is bigger than the standard deviation of B. So essentially what you can see here is that the values are closer or spreader from each other, more spread from each other. This has to do with the values for the standard deviation. Different scenario would be here with x and y. What happens with x and y? With x and y, what we have is that they have exactly the same shape. So what they have exactly the same shape, their standard deviations are the same, but one is moved, is translated to the right. For example, the x curve is the x curve translated to the right. What does that mean? That means that the mean is bigger in the case of y than x because it's moved to the right. It has a bigger value for x in that sense. So this is to understand what we talk about when we're talking about the mean and the standard deviation and how this would look like. You will not going to be working essentially with this. It's just a comment before we get on to the star of this first video, that is the normal standard deviation. In general, we're going to say that a continuous random variable x is normally distributed with mean mu and variance sigma squared. We're going to write it like this. X is distributed normally with mean mu and variance sigma squared. Now, we're going to define what we call the standard normal variable. What is the standard normal variable? The one that we're usually going to call by the letter Z is the one that has a mean of 0 and a variance of 1. It's like our simplest, like in a way to speak, normal distribution. Okay, the one that has the mean of 0 and the variance of 1. Why are we choosing mean of 0 and variance of 1? To make calculations easier. Okay, this is essentially why the standard became the standard, because it could make calculations easier. And as the line of symmetry is going to be in the value for the mean, the line of symmetry is going to be in my y-axis. It's going to be where x is equal to 0. So this is the graph for the normal standard normal deviation, the PDF. It has this beautiful formula here that I'm just giving to you as call it a fun fact if you want to call it somehow. You're not going to be using that, but you can see that is an exponential with a negative squared power and then some pi appearing over there. And this is how it looks like. We usually call it the Gauss bell. And we're going to be focusing mainly on our phi values. Okay, what is it that we call a phi value? Phi, for those who don't know, is this uppercase, okay, this Greek letter that we have here that we're going to be writing essentially with the uppercase phi. This graph here is known as the lowercase phi, and we're going to be focusing on the uppercase phi. What is the uppercase phi? The uppercase phi of Z is the value of the probability that Z, our normal standard variable, is less or equal to that value of Z. Remember that the equals here don't matter, so if you write this, probability that Z is less or equal than Z is the same as the probability that Z is less or less strictly than Z. These two probabilities are the same because the equal is always 0, so it's not going to affect anything. But the thing is that we're going to be focusing on understanding what this value is. This value is the area. Imagine that Z is around here. This value, probability that Z is less than Z, is going to be equal to all of this area that we have here. Okay? All of this area is the probability that Z is less or equal than Z. And that is our capital phi of Z. Okay, this is like the first concept that we want to understand when addressing the normal distribution, the standard normal distribution. Then we're going to be essentially at first finding probabilities from a value and upwards. Now, how is it that we find it? Because I mentioned earlier that we are not going to use integrals in this case. Integrating this is horrible. So how do we do it? We do it with the normal distribution table. This normal distribution table that I will be showing in full in a few more minutes is given in the list of formula and statistical tables for the exam, so you will have it. For those that don't have access to it now, you can go to my webpage where you can see the table that you will be given in the exam. And now I'm going to show you how to use it, because if you don't know how to use it, then it doesn't give you anything how to find it. So we're going to focus, for example, I'm going to give you the example of calculating the value for phi of 0.274. That's what I want to find. So how do I find that? Well, first, I'm going to take a look at my first and my second figures. 0.2. This 0.2, I'm going to go and find it, as you can see here, in this column that we have here. This column that says, sorry, this column that that is labeled as said here. You will go 0.1, 0.2, and here we have 0.2, the one that I'm looking for. Then for my third figure is a 7. You can see here that is a 7, so I'm going to go and look for this 7 in this row of values. In this row of values, I'm going to be looking for 0, 1, 2, 3, 4, 5, 6, 7, and I'm going to go to this row, that is the one that corresponds to the 0.2, and this column, that is the one that corresponds to the 7. So then I'm going to take this number. The number that I found here, that is 0.6064. Is that the probability that I'm looking for? No, not exactly, because I still need to use the 4, okay? How do I use this 4 that I have here at the end? Well, I'm going to go to this extra space here that relates to the fourth figure. How do I use the fourth figure? Well, I need to see what is my fourth figure. In this case, my fourth figure is a 4. So I need to go to this column and the same row that I was using earlier, and I have this beautiful 15. What does this 15 means? Means that I have to add a 15 at the end of this number. So what does at the end of this number mean? Means that I'm going to be adding the 15 in the last two places that I have here. Okay, so it's going to be this is going to be added to the 1, this is going to be added to the 5, and then I need to add another 0, and the first 0 to complete the number. Okay, this 15 is going to be playing this final role there. If the number is a single digit number, you're going to be adding 3 decimal zeros here. Okay, it's like the last digit that you're adding. So what is my value here? My value of the probability that I'm looking for is 0.6079. That is the probability. This is the same as the probability that my value of Z is less or less than equal, remember it doesn't matter, than 0.274. That is what I was looking for by finding the phi. Now remember that is also a measurement of an area. Okay, we're going to see how we can use that in a minute. So this is how to use the table, and now we're going to be doing some examples. We have more exercises in my webpage that you can access via the link in the description. So we're going to be doing some examples so that you can see other rules that apply in this case. So let's take a look at this. We are given that we're working with Z that is the normal of 0, 1 normal distribution, and how to calculate this probabilities here. So let's begin with the first one. The first one is the probability that Z is less than 1.23. What is this equal to? This is equal to the value for phi of 1.23. So what is it that I need to do? I need to go to my table. Let me go to our table and let's take a look at this. This is the normal distribution function table that you are given in the exam. This page that we have here is the one that you will be able to, you will have with you. You will be given a booklet with a lot of formulas and this table on one of the pages. So see how it is presented. Here you have that If a normal distribution within 0 and -1, then for each value for set, the table gives the value of phi of set. So they are telling you what they're giving you here. For where phi of z is the probability that z is less or equal than z. Everything that we have been talking about is explicitly told there with this beautiful diagram. And then you are also told, because here you will see that my values of z begin with 0, 0 and begin like on positive values. So you're told this first rule. If your z is negative, you can use 1 minus phi of z. Why is that? Well, this has to do with the following. If your z is negative, you will be going here, for example. I'm going to try to do it a bit more closer to the actual value. This, and then it will be somewhat around here. This will be my negative z. And this here, that we have this area that I'm shading here, this would be the probability that z is less or equal than negative z. Now, this area that I marked in red here is equal to this one that we have here. Because remember that the normal distribution is symmetric. So these two areas are the same. So essentially, this part here that is also equal to the probability that z is less or equal than negative z share an interesting relationship with this. Because all of this that we have here, as this is a PDF, all of this must add up to 1. So if you look at this part of the graph, this gray part here, this is the probability that z is less or equal than lowercase z. Try to make it as a lowercase here. Because this is the actual phi of z, right? The phi of z is all of this part. So all of these parts plus this red part has to be equal to 1. So you can solve the value for this negative phi of z by doing 1 minus the phi of the positive z. So essentially, if you have a negative, work with the positive and then do 1 minus that value. But that's the reason why. So now, yes, going back to our problem was finding phi. Remember, we're going to find phi of 1.23. So let's go over here and take a look at the table. We have to find 1.23. So how is it going to work? I need to first go to 1.2. 1.2 is here, so I'm going to be working with this row that is there. And then it's 1.23. So I need to use this column here. So I need to go to this row and this column. So the value that I'm looking for is here, 0.8907. So this value is equal to 0. And we said 8907. And it's just that. That is the probability that I'm looking for. It's quite straightforward. If you think of it, it's just going to the table and looking up the numbers. In this case, as we didn't have this fourth figure, we didn't have to use the add at the end. It was just looking at the first value. This may eventually happen. In some cases, for example, in case number 4, we're going to be using the add again so you can see it. But I believe that this one so far was okay. Let's take a look at number 2. And for number 2, you should notice that you are being told to find the probability that z is greater or equal than 1.23. So essentially, what we're doing here, I'm going to be making some drawings now so you can see what's going on. Oh, that's a horrible line. Let me use the straight line here. Here we have the x-axis and the y-axis. And now I'm going to draw the curve. I'm going to be doing my best with the curve. Okay, that's neat enough. We want to find this. We want to find, let's put 1.23 here. We want to find all of this area. Okay, because remember that areas relate to probability. So this is what we're looking for. We're looking for the probability that Z is greater or equal than 1.23. We already know all of this probability. I'm going to be drawing it in green now, in yellow. All of this probability, we know it, because this probability that we have here, that is the probability that phi is less than 1.23. This is the phi of 1.23, because it's less than. And remember that these two areas, the area in yellow and the area in green, must add up to 1. So as they must add up to 1, this probability that we're looking for here, plus the value for phi of 1.23, must be equal to 1, and hence the probability that we want, the probability that Z is greater or equal than 1.23, is equal to 1 minus phi of 1.23. This always happens, okay? This is a rule that always happens. The probability that phi is greater than a number is equal to 1 minus, the probability that Z is greater than a number is 1 minus phi of the number. Remember that phi is the number that we look for in the table. So how do we calculate this? Well, this is quite straightforward now, because the only thing we need to do is we need to go and take, well, it's going to be equal to 1 minus 0.8907, and this is equal to 0.1093. And that's it. That's the value for the probability. So you see that working with this normal table and this normal variable, it's not that complicated once you get the hang of it. It's not that challenging, but you may need to practice a bit at the beginning at first. Then let's do number 3. Maybe some of you want to do it by yourselves. If you think you know what could may happen here, you can pause it now. I'm going to be erasing my notes, and I'm going to be showing how to work with number 3. Number 3, and again, I'm going to be drawing a graph so you can see what is happening here. We have there and there, and the curve over, oh, let's do a curve there. Okay, that's not good. Oh my god, it's very horrible to draw these things, but okay, something like that would work. Here we have x, here we have y, and we want to find the probability that my Z is in between two values. This means that we're going to be working with two values for lowercase z. We're going to have over here, it's going to be 0.4. I'm not using any scale here, just for you to know. And then we have over here 1.7. So what is it that I'm looking for? I'm looking for the probability that my Z is in between these values, meaning that I want my area under the curve for these values. I'm going to draw that now in green, okay? The area that I want here is the one that I'm marking here in green. This is the area, this is the probability that my Z is in between 0.4 and 1.7. Now, let's think about it. If I consider my probability from this value backwards, that is my entire phi of 1.7. Now, but I don't want this and all backwards. I want this until here. So to all of this that I had, I want to subtract this part. But what is this part? This part is actually phi of 0.4. So essentially, this can be calculated as phi of 1.7 minus phi of 0.4. Because remember that phi of 1.7 was the area from this value backwards, all of this here, and then phi of 1.4 is this part that I don't want. So as I don't want it, I subtract it. How do we find these two values? Again, we go to the table. Let's take a look at phi of 1.7. Phi of 1.7, I'm going to be going over here. And in this case, my 1.7 is here. So I'm going to be using this row. And my next digit, as it's not given explicitly, is a 0. So I'm going to be using this number here, 0.9554. So this is equal to 0.9554. And to that, I'm going to subtract the phi of 0.4. What is the phi of 0.4? Again, as we have no value for the second digit, that's going to be a digit, is going to be a 0. So we're going to be using this value here, that is 0.6554. So this is minus 0.6554. This is a very easy like subtraction because you see that all of the decimal digits will cancel out except for 0.3, and that is the probability in this case. Okay. This is how it works when it has to do with finding the the area between two values. You just take the phi of the greatest value and subtract the phi from the lowest value. Okay, so essentially we have been covering so far everything. Now, there's the last thing for this video is what happens when the exercise is given the other way around. This says you have to find the value such that the probability that z is less than that value is this number. So in this case, we need to work it like the other way around. We need to find in the table the value that works. So my value is 0.9072. I'm going to go to the table. I'm going to write it here. I'm going to write over here that we're looking for the probability that z is less than a is 0.9072. I'll just write it there so I can have it. And now let's go to the table. The thing about this is that, well, in the best case scenario, you can find exactly that number in the table. Okay, you just go through them. You will see that numbers are ordered. So, for example, 0.90s are around here. They start here, 0.1915, and then they go all the way here until here, then you get to 0.91. So you know that you're going to be in between those values. Now, the thing is that you can see that this is not 9015, then we have 9032, 9049, 9066, and 9082. So we don't have exactly that value. We have one value that is a bit previous, and then another that is after that. How are we going to work? Well, remember that these probabilities are found by the number on this side of the chart, and then we're going to be adding something. So maybe what we need to do is we need to consider the number that is previous to that, and then see what we can add. As I was telling you earlier, the number that we have here that are closer to this are 9066, that we have it here, 0.9066. And then the next one is 9082. This one is greater than, so we're going to be focusing on this one here, 0.9066. I'm going to write that down over here. We know that we have an 0.9066. This value is going to be added to something that is going to give me 0.9072. What is that something? Well, that something is 0.0006, right? Because if we make this 6 plus this 6, it gives you 12, so we get a 2, we add a 1, so this 6 plus 1 is 7, and we get what we're looking for. So what we know from this value is that we need to add a 6. What does adding a 6 mean? Well, we go to this table, with this part of the table, with the add that we have here, and we know that we must add in this row a 6. Okay, we want to add this 6 that we have there. So which is going to be our value for A now? Well, we're going to take a look on which values we are using. First of all, we're in this row. So my value for A is going to begin with a 1.3, okay? Then I'm using this column here that corresponds with the 2. So my number is going to be 1.32. And then I'm going to add a 6 that is in the column of the 4. So my number is going to be 1.324. 1.324. That is the value for A that I'm looking for. I'm going to write it down here. My A is 1.324. Why is 1.324? Because it's 1.3 from here, then the 2, and then the 4. Okay, it's a very interesting exercise to do. As always, you have more exercises in my webpage in case you want to practice with this. I'm going to be recording 2 more videos on this topic. The next one is going to be about standardizing. This is how we can use normal distributions when the mean is not 0 and the variance is not 1, because clearly you're not going to have one table for every different mean. So it's just going to be this one table, and you're going to learn how to convert everything to this. And the last one has to do with a connection that has the binomial and the normal distribution. So I hope to see you in those next videos. As usual, if you have any comments or just suggestions, use the comment section, and check my webpage for more explanations and exercises. As usual, thank you for watching.